so we're in section 12.4, and we're talking about angles and segments. In circles. So the first thing we need to talk about is a new kind of, we're going to give a name to a new kind of line that intersects a circle. So we call a line that goes through a circle in two places. This is called a secant line. And secant comes from the Latin meaning to cut. Secant means to cut. So this line cuts through the circle. Secant lines aren't diameters, they don't go through the center. And then inside the circle, the little piece that's inside the circle would make a chord. So the line itself is a secant, and then inside the circle we end up with a chord. So we're going to be talking about secant lines in circles today. So our secant line intersects a circle in two places. So what we're interested in is the angles that are formed when two secant lines cut through a circle. So our first case is going to be when the vertex is inside the circle. And we want to know how the angles and the arcs are related. So here's our picture. We're going to have two secant lines cutting through this circle. So we have something like this. And the vertex is inside the circle. And I'm going to call this arc x degrees, this arc y degrees, and this angle 1. So for these, we're saying our vertex is inside the circle. It's not at the center. So our center of the circle is going to be here. So we mark the center of a circle with a dot. So we can't say, oh, they intersect in the circle, so it's the center. Not at the center, not on the circle. So our rule when we have our vertex inside the circle, measure of angle 1 equals x plus y divided by 2. And the way my shorthand, I like to think of this in the shorthand, the angle equals the arc plus the arc divided by 2. So our angle equals the arc plus the arc divided by 2. And the arcs we're talking about here are our intercepted arcs. So that's our first rule. We could also have two secants that intersect outside the circle. So our vertex would be outside the circle. But questions before we move on? So this is our first big thing that we're talking about today. Angle equals the arc plus the arc divided by 2. All right, our vertex outside the circle. And this can happen in several different ways. So let me draw 3 different pictures. We could have two secants. I'm going to call this x degrees, y degrees, and this is angle 1. So I could have two secants. The other way this could happen is where our vertex being outside the circle, we could have a secant and a tangent. So this is a tangent line here, and this is going to be x degrees, y degrees, and angle 1 is this little angle inside here. Or we could have two tangents. So here's my third situation. And this is going to be x degrees, y degrees, and angle 1 right there. Didn't see anything. I looked. Yeah, I looked down that row. Didn't see anything. So all of these three ways are ways that we could have a vertex outside the circle where we have our angles that we have angles and arcs involved with our circle. We have one rule for all three of these ways. When our vertex is outside the circle, the measure of angle 1 equals x minus y divided by 2. And my shorthand here is angle equals the arc minus the arc divided by 2. So when a vertex is outside the circle, the angle equals the arc minus the arc divided by 2. And all three of these ways, my vertex is outside the circle. So, two pretty easy rules here. Questions so far? All right, let's look at a couple of examples here. It's important to remember we're not talking about, these are not central angles. Our vertex is not at the center. They're not inscribed angles. Our vertex is not on the circle. So those two cases are different. So we're doing something a little different than we've done before. All right, so a couple of examples. Start off with an easy one. There's my circle. I want to get rid of my arrows. I'm just going to do this. And this is 87 degrees. This is 165 degrees. And this is angle x. And the problem asks us to find x. So we have the vertex inside the circle. So when the vertex is inside, we know that the angle equals the arc plus the arc divided by 2. So our angle is x. X equals 165, one arc, plus 87 divided by 2. Plug that in my calculator, and I get x equals, when I plug this in, this is 252 divided by 2, so x equals 126 degrees. So nice easy example there. Angle equals the arc plus the arc divided by 2. Are we good there? All right, let's look at another one. Little more complicated, but this not too bad. So here's my setup here. And I'm going to say this is 98 degrees. This arc is 98 degrees. This arc is y degrees, and this angle is 22 degrees. So we have our vertex outside, and we want to find y here. Our vertex is outside, so our angle equals the arc minus the arc divided by 2. What is our angle here? in this setup? What's our angle measure? Is y the angle or is y the arc? What is it, Matt? 22 degrees. Our angle is 22 degrees. So I'm going to write that 22, the angle, equals the big arc, 98, minus the small arc, y, divided by 2. So I'm just plugging the things into their correct places in the formula. The angle is 22, so I put that there. The big arc is 98, the small arc is y. So I plug everything into their spot in the formula, and now I need to solve for y. All right, so how do I get rid of this 2? Multiply everything by 2. I'm going to multiply this side by 2, multiply this side by 2. Those cancel, and I get 44 equals 98 minus y. I'm going to subtract 98 from both sides. 44 minus 98, I get negative 54 equals, and I have a negative y. So what does this tell us? Y equals, to get rid of that negative, I can multiply both sides by negative 1. Because I don't want negative y, I want positive y. So I multiply both sides by negative 1, and I get y equals 54. So I have negative y equals negative 54. To get rid of those negative signs, I multiply everything by negative 1. Questions there? All right, so just to look back at this one really quickly, sometimes they won't be asking, the problem won't be asking for the angle, or won't be asking for, so it won't be asking for the angle. So you just plug in the pieces that you know into your formula and solve for the pieces that you need. We've done this a lot over the course of the year. Plug in what you know, solve for the part that you need. All right. So now let's move from looking at arcs and angles to looking at the lengths of these segments that we get when we have our secants and tangents intersecting on circles. We're going to talk about segment lengths. So we're going to talk about 3 different situations here. The first one is when we have 2 chords. I'm going to call this A, B, C, and D. And these are talking about the lengths of the segments. A, B, C, and D are the lengths of these pieces of the segments. When we have 2 chords intersecting in our circle like this, the lengths are related by A times B equals C times D. And the way I think of this is the part times the part equals the part times the part. So I multiply one part here by the other part, and that equals one part here times the other part. Part times a part equals a part times a part. Just trying to come up with a way to remember how this works when we have these things. So that's one way we could have our intersections here. Another way is if we have 2 secants. So if we had a situation like so, A, B, C, and D. And these are the lengths of these segments. So here we have 2 secants. And this one, Our lengths are related. A plus B times B equals C plus D times D. And what I remember here is the whole. A plus B is the length of that whole segment times the outside. B is the outside part, the part that's outside the circle, equals the whole times the outside on the other piece. So the whole times the outside equals the whole times the outside. A plus B is that whole length. C plus D is that whole length. So that's how this works when we have two secants. And then the last setup we could have would be a secant and a tangent. So let's look at that one. So our circle here, and we're going to have a secant, a tangent. I'm going to call that A, B, and C. So here we have secant and tangent. So when we have a secant and a tangent, for this piece it's exactly the same as the last one we talked about. A plus B times B equals C squared. And what I say for this one is the whole times the outside equals the tangent squared. So we have three ways that we can find the lengths of segments. Two chords. They intersect inside the circle. We have the part times the part equals the part times the part. We just multiply the pieces of the segments together for one segment, and that equals the pieces of the other segment multiplied together. Vertex outside the circle, two secants. The whole times the outside equals the whole times the outside for that setup. And when we have a secant and a tangent, whole times the outside equals the tangent squared. All right, so let's look at a couple of examples here. Here's our circle. And we have these segments. Let's say this is X and 12 and 14 and 11. And we want to find X. So here we have two secants. We're going to use the whole times the outside. Whole times the outside. So what is the length of that whole segment? How do we find the length of this whole segment? X plus 12. We add those two pieces together. X plus 12. So X plus 12, and I'm multiplying that, so I'm going to put parentheses, times the outside part, times on this piece. So the whole piece is X plus 12, the outside part is 12. And on the other piece, what's the length of this whole piece? 25. 14 plus 11, 25. So the whole is 25 times the outside part, 11. I'm going to distribute here. So 12x plus 144 equals 25 times 11. Remember our little trick? Separate the two numbers, 2 and the 5, and add them together, 275. Subtract 144. So 12x equals 275 minus 144 is 131. Divide by 12, and x equals 10.9. All right, questions there? All right, one last example. So here's our picture on this one. This is 9 and this is 6, and this is x. And we want to find x. So here we have a secant and a tangent. So we are going to do the whole times the outside equals a tangent squared. So how long is this whole piece? 15. So I have 15 times 6, the outside part, equals the tangent squared, x squared. 15 times 6 is 90, so I have x squared equals 90. So we're going to take the square root of both sides to undo that square. And I get x equals the square root of 90. I can simplify this if the problem asks us to leave it in simple radical form. This is the square root of 9 times 10. And I get 3 square root 10. Or if I plug this into my calculator, x is approximately, if I round to the 10th, 9.5. All right, we good on that example? All right, let me back up here really quickly. So our two main ideas here. When we're looking at arcs and angles, when our vertex is inside the circle, the angle equals the arc plus the arc divided by 2. When our vertex is outside the circle, no matter how it happens, our angle is the arc minus the arc divided by 2. And then we have our rules for segment lengths. So we're just looking at the lengths of the segments. We're not worried about angles and arcs. Two chords, part times a part equals a part times a part. Two secants, whole times the outside equals a whole times the outside. Secant and tangent, whole times the outside equals a tangent squared. All right, homework. So we have page 794, 8 through 26 even, 32, 34, 35. Common Core week 24, due block day. Extra credit that's up here on the table, due Monday. Graded for accuracy. Final review. Paper and pencil, and online. Both due the day of the final. The end of chapter review, the online one is graded for accuracy. It automatically grades it. The pencil and paper will be graded for completion.